All right. Thanks everyone for coming to the second colloquium or third colloquium talk this semester. And today we're really excited to have Dr. Ranjit Jhala, who's going to be talking about language integrated verification. And he is a professor of computer science and engineering at the University of California in San Diego. And his research area is generally in algorithms and tools to help engineer reliable systems. And he's been doing a lot of work in different areas, so model checking, program analysis, automated deduction, and type systems. He's probably best known for a number of different tools, especially Liquid Haskell and the BLAST software model checker and things like this. And so we're really excited to have Ranjit here. So thank you.
Okay, well, thanks, Harley. Can you hear me? Is the audio all good and whatnot? Okay, well, thank you very much. Thanks for inviting me to speak at your colloquium. So I'm going to tell you about a line of work that I've been sort of working on with my students and collaborators and colleagues for, I guess, more than a decade now, which I sort of broadly speaking call language integrated verification. But I'm guessing this is a fairly broad audience, so I want to give you a little bit of background on what I think much of modern programming languages research is about. And so this is a bit of a strange analogy, but bear with me for a second. So this, of course, is George Orwell, author of lots of fantastic books. One of my favorite books is, and probably many of yours as well, is 1984. And you might remember that one of the kind of central themes in 1984, one of the many amazing themes of 1984, is this whole notion of the power of language, where, here's one of my favorite quotes, where the guy says, we want to design a language that makes thought crime literally impossible. There will be no words to express it. So in a sense, I feel much of modern programming languages research is guided by this particular quote. Except it's not so much thought crime that we want to make impossible. We want to make errors in code literally impossible. What my friend Andy Gordon at Microsoft likes to call the war on error, right? We want to make it impossible to just introduce errors in your program. We want to make it so that the programs you write are fast and correct and don't have security holes and so on and so forth. So now over the past, 50 years or more, there've been a suite of really wonderful technologies that, that computer scientists working in this general space have come up with. These include modern decision procedures, the method of abstract interpretation, data flow analysis, proof assistance, program synthesis, model checking, so on and so forth. But, if we are to be entirely honest with ourselves, I would say that these have had they have not really had the kind of impact and they haven't seen the kind of adoption that I believe they ought to see. And what I mean is, the comparison I'm making is with tools like, for example, profilers, gprof, or garbage collection, or version control, or debuggers. These are kinds of tools that programmers use day in and day out. This is just part of the software development process. And so, I've been kind of scratching my head. Why is it that tools like profilers, so on and so forth, have seen so much adoption, and yet all these advances in program analysis and verification are yet to get to that point. So I have, there's probably many different reasons for this, but I have my my favorite hypothesis is the following: is that one of the things we've not done correctly is we've sort of split the world of developers into two. We've partitioned them into the person on the left, who I'm going to call the programmer, and the person on the right who's like the verification expert. Okay, so people like me and perhaps like Harley, right? We're the people who know how verifiers work, and there's everyone else who writes the actual programs. And we've kind of set up this weird wall between the two of us. The programmer writes the programs, and the verifier's job is to kind of come after the fact and tell them, yes, your code looks correct. We've sort of proved various theorems about it. And I argue that this particular wall is really quite counterproductive for various reasons. First, most importantly, the programmer can't actually influence the verification. They just write their code, and they can't actually change how the verifier works. They can't kind of give it hints and so on. Perhaps even worse, the verifier can't influence the program. There's this weird kind of temporal dependency where the programmer writes a thing, verifier kind of stamps it. But what you really want is for the verifier to influence how programs are written in the first place. And so what I want is to move from this world of program analysis and verification into programmers analysis. I want to kind of unify these two people into a single person who does their verification during development, not so much worries about looking for bugs after. That's important, and that's kind of a stepping stone for where we want to where we want to go. But really, I want to kind of build a tight integration between these two, right? So that the program can influence the analysis, can give the analysis hints, can tell the analysis what is interesting, and the analysis can kind of influence the program's design. Now, of course, you might argue that, I'm kind of I'm an academic and I would, these are all kind of wishful things that one wants in one's ivory tower. But in fact, over the last few years, there's been a lot of research from large companies that seems to indicate the same kind of need. So here are some examples. So what I want is for the analysis to influence the program's design. And in the program analysis of the programming languages world, we always have this concern that there's a kind of spectrum in your analysis of how precise is your analysis. Does it actually report real errors, or does it only produce false alarms? And I argue that this kind of obsession misses a very important dimension, which is at what time was the actual report, was the error pinpointed? And I argue that something that if you reported it really, really soon in the development process could have been construed as a real error. If you report it, a few days after it was written or a few weeks or months, then it kind of becomes a false alarm and its utility diminishes, right? And there's a bunch of evidence that supports this claim. So for example, in 2017, my friend Manu Sridharan, who at the time worked at Uber, developed a null pointer checker using Michael Ernst's fantastic checker framework. There's a framework for Java that lets you design sort of plug-in bespoke type systems that are, that catch particular properties of interest in large Java programs. And so Manu wrote a null pointer checker based on it. And Manu found that, they deployed it at Uber, and they found that, when they provided the feedback quite late in the process, right? During a kind of a post-code review. This late feedback could lead to a frustrating experience. The developers change, could pass code review and all that stuff. And it was only rejected much further down, even though there was a very simple fix, right? There's a similar kind of study done at Google by Caitlin Sadowski, who leads the program analysis team there, where they found that Google developers perceive issues flagged at compile time, as opposed to patches or for checked-in code, catch more important bugs. Survey participants deemed that 74% of the issues flagged at compile time were quote-unquote real problems, as opposed to just 21% after. And here's an even more startling number from some friends at Facebook. Cristiano Calcagno and co, who built a really kind of sophisticated program analysis that checks for various kinds of memory errors and memory leaks. What they found is that when they first did a batch deployment where the analysis ran overnight and produced bug lists that were sort of shown to the developers the next day, nobody was interested in fixing those errors. The fix rate was like 0%. Then when they switched their analysis so that it worked in a kind of incremental mode where the reports were produced during code review, it was the same warnings, but now they were fixed at 70%. So they were just like shocked. Wait, it's the same thing we're telling you, but we're telling you this much earlier. And that completely changes the game in terms of how valuable the reports are perceived, right? So that's one half of the equation. The other important half is that I want ultimately not for the program verifier to be, on the other side of the wall, unable to see what's going on with the program and unable to actually learn any hints about what the program is doing. What we really want is for the program and for the programmer to themselves be able to control and influence the analysis itself. In particular, I want the programmer to tell the analysis what is important to be analyzed in the first place. What are we looking for? So null pointer dereferences are fine, but there's a whole world of other things beyond that. And further, I want to give the analysis hints on how to actually do the verification, right? That might be somehow custom or tailored to the program that's of interest. So what to analyze? We can start with something like null pointer dereferences, and you can kind of imagine a continuous spectrum. So some of these are problems that, essentially want to check for, in every program, null dereferences. There shouldn't be memory overflows, array bounds, or violations, so on. There shouldn't be integer overflows. But then as you kind of move on, you might want to enforce various user-defined properties. Maybe you have some specialized data structure on which you want to express some check, some invariants. Maybe you're building a web application, and in that web application, you want to make sure that only certain users are allowed to access certain kinds of resources. For example, only the instructor of the class or a particular student should be able to view the grades of that student, not your student, the student's friends, and so on, right? Until you sort of at the very limit have kind of full quote unquote functional correctness, where you can write a separate specification on exactly what the code should be doing, and you can verify that against your implementation, right? For example, the most celebrated example of this over the last 15 years is probably Xavier Leroy's formally verified compiler for the C language, which is just, I mean, it's one of the most amazing feats of engineering, I would say, of the last 20 years. Okay, so how are we going to do this? How are we going to kind of integrate verification and languages? And let me kind of sketch this line of work that I've been doing over the last decade or so that tries to bring these two things together, right? Hopefully, this has given you some motivation for why we want to integrate languages and verification. Next, over the course of the, I guess, remaining 40 or so minutes, what I'm going to give you is a kind of an overview of one approach for building this kind of language integrated verification. And then hopefully I'll have a few, 10 minutes or so at the end to tell you about some lessons we've learned over the course of the last, of all this work on what I think are, what are some things that are easy and what are some things that I consider to be really the most difficult problems in this space. Okay, so let's, let me get off my soapbox, as it were, and let's jump into the kind of technical part of the talk. And let me tell you this approach that we've been developing for how to build a language integrated verifier. And I'm going to break it up into 3 parts. We'll probably have to skip the proofs part. So let me just start with how do we even get the programmer to specify what properties they want to check? And then I'll give you a quick overview of how the verification works. It's going to be really fast. It doesn't really matter if you don't get all of it. It's kind of compressed, so don't worry too much about it. Just want to give you a flavor, okay? Okay, so let's talk about what kinds of things might the programmer specify about their code, and how can they kind of give the code, give the analyzer hints on how to verify them, okay? So the approach that I've been working on uses what is called refinement types. So what we're going to do is we're going to take types, as you know them, int, bool, string, so on and so forth, and we're going to refine those types using mathematical logic, okay? So let me give you a concrete example of what this looks like. So a refinement type at a very high level looks something like this: x colon b such that p. So think of it as, what this says is the set of values x that are of type b such that some predicate p is true. So that's a bit abstract. Let's look at a concrete example. This p is going to be from a mathematically kind of a decidable logic. So it's from a logic that is decidable using what are called SMT solvers. Just think of them as fast decision procedures that can fully reason about formulas in this logic. So here's a concrete example, right? I'm going to say, here's a type of natural numbers where the natural numbers can be defined as the set of integers I, so I colon int, set of integers I, such that I is greater than or equal to 0. Okay, so by the way, just a pedantic point, I'm going to keep saying greater than because it's a real mouthful to say greater than or equal to. So I hope you will forgive me for that. But I really mean the set of non-negative integers, okay? Okay, so that's the set of natural numbers. Now let's see how we can specify more interesting things like how can you use refinements to talk about array bounds and then integer overflows and then use the defined invariants. Let's start first with array bounds. So in order to explain how array bounds checking might work in a language integrated verifier, I'm going to look at the kind of the classic example that sort of illustrates array bounds checking, which is just plain binary search on an array. So I'm going to be showing you code snippets from this liquid Haskell system that Harley just mentioned. So all the code is in Haskell, but I'm going to kind of explain it. For those of you who are familiar with Haskell, fantastic. For those of you who are not, don't worry too much. The code snippets we'll see should look quite familiar to how binary search, for example, would look in another language. So here's binary search. It's a function, top level function, binary search. We're looking for a value v inside a vector, and vector is what the Haskell people call arrays. That's their fast array library, right? And remember, the goal of binary search is to return the position at which the value v occurs inside the array. And it returns a maybe, which is, think of it as an optionally null value, because the value v might not actually appear inside the array, right? So if it doesn't appear, then we return nothing. And if it does appear, then we return just of whatever that value is. So think of it as either returning null, think of nothing as null, if you like, and just of mid as essentially the non-null integer containing where position where the particular value appears. Okay, so let's just look at the high level structure, right? So if you recall how binary search works, you have the array, which is called vec here. You have the value v, and you always maintain 2 pointers, a low and a high pointer, and you compute the midpoint. And then what you do is you test, you check, is the value that I'm looking for, you look at the vector at that midpoint. So this exclamation mark, think of it as what in Java you would write vec in box brackets at midpoint. If the value that I'm looking for is less than the midpoint, then I recurse on the left, right? I update the midpoint, I recurse on the left. If it's greater than the midpoint, if the value is greater than the midpoint, then I recurse on the right side. And otherwise it's equal to the midpoint, so I can just return that. Okay, so pretty straightforward, right? It's just pretty standard binary search, nothing fancy going on. Now, since we're using arrays over here, look at this, there's an array access. Let's see how we can specify. How can the programmer tell the system, I would like you to verify that there are no buffer overflows, there are no array overflows in this particular code. So let's see how to do that, okay? So if you look at this code, you'll see there are 2 places that we're actually manipulating, we're accessing the array. The first is we're using this length function to compute the high index, right? The low index is 0 and we want the high index. We're computing that with the length function. And of course, the second place that we're using the array, we're accessing the array, is this exclamation mark or bang operator, which is the index function that returns the value of the array at whatever that mid was. Great. Now let's see how we can tell the system to verify that there are no array overflows. The way we're going to do it is by assigning special types to the length and the index function. So here's what the type of the length function looks like. It says the length takes as input a vector v, okay, that's what this is the input, and it produces as output, that's what I'm highlighting in blue over here, a natural number n, remember the length can't be negative, it's non-negative, right? A natural number n that is equal to the length of the vector v. So that's what this logical predicate says, n equals vlen of v, where think of vlen as logically describing the size of the vector v. Okay, so this is what, if you're familiar with program logic, this is what is called a post condition, where we say the output value equals the input vector's length. Next, let's look at the index function. So here's the exclamation mark, right? What index does is it takes as input a vector, again, let's call it v, and it takes as a second input the index I, at which I want to get whatever the value of the vector is. But now I'm specifying a precondition on I that says that I must again be a non-negative number, right? You can't specify a negative index because that would definitely be out of bounds. And further, I must be strictly less than the len of v, okay? So I specify this now as what is called a precondition that the index is between 0 and the vector's length. And now that we have these 2 preconditions, we have these 2 type specifications for length and index, the verifier says, oh, that's what you're interested in, I'll take it from here. So here's a little screen video that explains what happens. I would tell it, hey, these are the 2 things I'm interested in. In reality, of course, those 2 specifications would be in a standard library, right? Which I would just use automatically. I'm putting it into this video just to show you. And once I tell the system, hey, assume this about the index function, assume this about the length function, does this hold of my code? The system comes back and says, no, I don't think so. There are 2 out of bounds errors over here. When you access the vector at the midpoint, I think that access could be out of bounds. And now this is a bit of a puzzle. So really, this looked like a perfectly legitimate, binary search. What could possibly have gone wrong? Well, if you scratch your head and think about it for a little bit, what you'll see is there was in fact a mistake. Right up at the top, we should have checked that the vector was in fact not empty. If the vector size was 0, then guess what? We would have accessed at the midpoint, which is index 0, and you would have gotten this weird off by 1 error, okay? And so now, and the thing I showed you was literally a video of me kind of programming this, right? So what the programmer would do is come back and say, oh, okay, right. Here's how you fix it. Let me just check over there that the vector is in fact non-empty. And furthermore, that upper index needs to be length of the vector -1. And of course, if the vector is empty, then return null, because obviously the empty vector can't contain v. And once I put this check in, lo and behold, the type system says, oh, okay, in that case, there are no errors. Okay, it's all good. We've kind of checked your program. The access to mid and so on is just fine. Okay, so that's pretty neat. So that wasn't so bad. You know, we were kind of talking because we got the feedback so quickly. You can just, oh, right, I forgot the off by one check. I fixed my code. Everything works just fine. Okay, great. Let's now move along and look at a slightly more interesting specification. So I'm going to keep working with binary search. But suppose now I want to say that there are no integer overflows. So how can I how can I tell the verifier, hey, you know what? I'm also interested in you telling me if there's any integer overflows in my code. So let's see how we would do that. So to do that, what we're going to do is we're going to take the types of plus and minus. These are the operators that literally just work on integers. And we're going to do sort of, we'll track overflow inside the types. So let's see how to do that. First, what I'm going to do is I'm going to define a set of bounded integers. Okay, so I'll say that a bounded n is an n that's between 0 plus maxint and between negative maxint and positive maxint. That's really what this is saying. Okay, I'm going to define the set of bounded integers, and then I'm going to tell the system, okay, from now on, you should assign plus and minus types that say that the inputs x and y that they take must be bounded integers. Okay, so you must only call me with values x and y such that x plus y and x minus y are both bounded. Okay, if they're not bounded, that should be a type error. And of course, if they are bounded, the value that you should return should be the mathematical addition or subtraction of x and y respectively. Okay, so I'm going to sort of package this specification back to our little binary search. I'm now going to tell it, hey, since I'm interested in arithmetic overflows, please use the specifications that I described in this bounded package. And the moment I do that, the system's like, oh, well then, in that case, all these operations might overflow. If I take the length of vec and I subtract one, that might overflow, and you add low and high, that might overflow, mid minus one, that might underflow, mid plus one might underflow. And so this is the kind of thing where the programmer would tell the analysis, oh, don't be silly. How could these possibly overflow? All these values, low and high and so on, these are all bounded by the size of the vector, right? This is just take the length of the vector. It could be 100, 1,000, a billion, whatever it is. Clearly, it's within the valid bounds of of the machine integer. And so what I would do is I would give it this assumption. The programmer would tell it, okay, look, values of the sizes of vectors are always bounded integers. Okay, so here's how you might specify that. I would say blah, 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 blah. For every vector, assume that the length of that vector is a valid bounded integer. Okay, so sizes are all bounded, vector sizes. The moment you do that now, all the little plus one, minus one errors go away, but you're left with this peculiar thing over here, where we do low plus high divided by 2 to compute the midpoint. Now, some of you might know this already, but this is actually one of these kind of famous gotchas, okay? So the midpoint, if you write it this way, can in fact overflow. And there's a famous blog post, you can Google this, by Joshua Bloch, who is, an author of many of the widely used Java libraries, where this is literally the title, nearly all binary searches and merge sorts are broken. And he has this very nice write-up describing it. But here's the deal. If you go back, here's how he says you should fix it. Instead of saying low plus high, you should compute low plus high minus low divided by 2. And the moment you do this particular fix that Joshua recommends, the type system says, okay, well then in that case, there are no overflows, okay? And so this is how, essentially, you're getting this kind of very rapid feedback inside your IDE or editor or whatever, where the programmer kind of gradually ratcheted up the different specifications that they care about. And the system quickly gave them feedback on, oh, by the way, you should probably tweak that and you should probably change this. And essentially, you're getting the system to do a code review with you as you go. Okay, great. Let me next sort of switch gears a little bit and tell you how exactly all of this happened. Okay, so everything you saw was just, how you interact with the system. Let me pause here for a moment and tell you a little bit about how verification happened. But actually, let me pause here for a meta note, which is, Harley, I don't know what the kind of interaction mode is. Do you want people to just block and raise their hands if they have any questions, or should I pause right now if there are any questions that people have?
Sure. I mean, it's pretty open. Most of the time, people are allowed to just say, hey, I have a question, or you can raise your hand and we'll try to make sure you respond.
Right. Okay, so let me just, okay, so good. So please just, I should have said this at the beginning. Yeah, just like, if you want to stop, just block, just like, you probably want to unmute yourself because I can never see the raised hands thing. I still have not cracked that puzzle in Zoom. But if Harley can see the raised hands, he can also just like say so-and-so has the question. But let me pause here in case there are any questions. Ooh, there's a little chat thing, but I've already noted someone has, are you able to verify any condition on the predicate of the refinement? So that's a great question. So I think the word any here is doing a lot of work, and I'm not entirely sure what you mean by it. I'm going to try and understand your question. So Paolo asked this. I think what you mean is, are there restrictions on what you can put inside the predicate in the refinements, right? And the short answer is yes, there are restrictions, but the long answer is no, there are no restrictions. So what that means is, the short answer is, if you want the verification to be completely automatic, where this SMT solver, the decision procedure, just like checks all your types for you, then you need to restrict yourself to this decidable logic. And in particular, we use something called the quantifier-free logic of arithmetic and uninterpreted functions. And there's a couple of other theories that you can kind of stick in there while ensuring things are decidable. But in more recent work, and this is what's in this third part, proofs, you can essentially start writing user-defined functions. You can just start writing random functions. Well, not random, but pretty arbitrary user-defined functions. And you can start using those functions inside your predicates. And this really kind of blows open the door where you can essentially start encoding pretty much whatever you like inside the refinements. But if you do that, then often you have to do a fair bit of work to you have to give the system hints on how to actually do the proofs, okay? So I don't think we'll have time to really talk about it in the course of this, but we can talk about it after the talk. I can kind of give you some explanations. Let's see, here's another question. In the array example, there were two similar checks, if low less than high. To fix the empty, we added a third one. I would be tempted to refactor this to lift it, but that would probably how can I refactor invariance while refactor code? So that's very interesting. Well, that's a good question. So for the most part, and we'll see some examples of this, we'll see one example of this. Since the system is kind of synthesizing the invariance, so if you look at it, the only thing the system really cared about is that whenever you do access an array, it is less than the length of the vector. How you establish that is up to you, right? So in this particular case, we established it just using this kind of standard style. The system is able to kind of pick up, wherever you use branch conditions, they're like, oh, that's what you're doing, so on and so forth, right? So in a sense, thanks to the type inference, this refactoring of invariance kind of happens automatically for the most part. But there are situations where if you try to do something that's especially clever, then maybe you have to say, by the way, over here, here's what I did, right? And in that case, you would have to specify a type signature yourself. So we didn't have to do that here because the system automatically, you put in that check over there, so it changes the invariance that it's learned about what the program is doing. How come you didn't have to write a refinement type for ints in the signature of the binary search function? You know what? I should have read Alexander's question before I answered Galley's, because in fact, that is the answer to Galley's question. Precisely. So I'm going to explain that when I talk about this verify, Alexander. So hold on to that thought for just a second. One of the cool things that happens with the verification is that we are going to synthesize those refinements. So I should point out that even though we synthesize most of the refinements, in reality, when you write a library, if I have a library function, I don't know what inputs that function should be called with. And for those, you would have to actually write down the refinement type in much the same way we wrote down the types for for length and the index function, right? So that's how you would have to write those down. But in this particular case, we didn't, because the system basically automatically synthesizes those. Think of it as what happens is in the binary search, it says, oh, you can give me whatever array you like. You can give me whatever value you like. This works. And the reason it works is because the programmer put that check in, right? So you have two options. Either you put that check into the code that, by the way, I'm testing that the array is not empty, or you put it inside the precondition for binary search that says, please only call me with non-empty functions. So it's up to you. Do you want to be, sort of program in a defensive style? Whereas I think Windsurf says, or was it Bob Kahn? I forget. Be permissive in what you accept. Or do you want to kind of specify in the contract, please don't give me empty arrays. I don't want you to do that. In which case, clients of binary search or places where you call binary search, they would end up checking that you won't always pass in non-empty arrays. Okay, so these are both fantastic questions. Okay, great. So let's move on and see a little bit how the verification works. And I'm going to be very, very fast. Oh gosh, I'm like 20 minutes past where I wanted to be. So whatever, it's fine. It's all good. Let's see how the verification
it's
works.
Cool. Even if we go slightly over, it's not a big deal.
Okay, great. Thank you, Harley. Okay. So everything we've seen up to this particular point is pretty kind of, you know, what programming languages people call the classic sort of Floyd horse style verification, where you have preconditions, functions should be called with inputs like this, and post conditions, functions will return values that look like that. And, you know, these ideas go back like more than 50 years. So Bob Floyd in 1967 wrote this paper, and there are no types, and, you know, they didn't have types, I guess, in two senses of the word. There were like no types, and there was no type setting either. Check it out. It's all like written by hand with these little dashes and flowcharts. Very old school. But if you squint at it, you know, this is like a program that computes the sums the integers from 0 to n or whatever, right? These little squiggly things over here that he's got in his handwriting, those are what we're now sticking inside the mathematical logic, right? The blue refinement predicates. But, and you know, this basic idea is in several tools, most notably ESC Modular, ESC Java, and Daphne from Microsoft, and now at Amazon. And many of these ideas go back to, you know, the mid 70s. They were sort of in the Stanford Pascal verifier, where you can write these pre and post conditions. I should point out, for those of you who don't know this work, Greg Nelson essentially was the man who invented many of these modern algorithms for decision procedures. And his kind of decision, his PhD dissertation from the early 80s is kind of like the landmark text that modern SMT solvers are all based on ideas in Greg Nelson's PhD dissertation. But what we also have figured out, you know, the contracts sort of work nicely, but they're kind of limited to the kinds of programs that one would write, you know, in those days, right? So very simple kind of first order procedural programs. Once you have more modern programs of the kind one writes, you know, in the 21st century, you actually need a little more sauce, okay? And what I'm going to describe to you next is what I like to call a kind of type-directed abstract interpretation. And it doesn't matter if those words don't mean anything. I'll try and give you a quick overview of how it works on a very, very small example. So here's a tiny example. It's literally a line long, but it shows you how modern languages have a whole bunch of stuff packed inside them, where the analysis has to be very, very clever in order to verify even something as simple as array bounds checking. So suppose I want to write a function called sum of squares that takes a vector of doubles, like floating point values, and takes each element in that in the vector, squares it, and then adds it all up. Okay, so this is, you know, I'll show you code that's written in Haskell, but the Python code would look basically the same, except there'd be def in a couple of places, right? So here's what the code looks like. Sum of squares takes x, and I have a library function called sum, and check it out. So what I do is, oh, let me minimize that pesky window so I can actually see my slides. What I do is, it's what is called a for comprehension, right? You might have seen this in Python. You can read this as, for each I in 0 to the length of x, take x of I, square it, and that gives you a collection, which I'm writing in this box bracket, and then call the sum function on it, right? This code looks pretty much the same, regardless of whether it was Haskell or Python. Oh, sorry, I pressed this again. The thing I want to emphasize is, actually, there was an off by 1 error. If you forget the -1, there's a buffer overflow, and when you put it in, the system's like, oh, okay, then it's all good, right? So now it turns out that in order to verify even something as simple as this, you need a fair bit of machinery. Okay, so let me explain why that's the case. So this is what you as the programmer might have written, right? It could even have been in Python. It doesn't really matter. But internally, this code gets transformed into something that looks like this. Okay, so let me kind of walk you through it slowly. So sum of squares takes some value x. What it first does is it computes a range. It calls this range function, okay, that takes a low and a high, let's call them n and m, and it returns a collection, a sequence of values between n and m, okay? So again, this is much like range in Python, takes a low and a high, returns this collection. Then what happens is that, so this low and high are used to generate this collection of values. Then what happens is that this simple innocent looking expression, x at I squared, actually gets turned into a lambda function, into a closure, if you will. Let me just call it body, that takes a parameter I, and for each I, it computes x of I squared, okay? And finally, what happens is we call a map function, where you can think of map as iterating. It's a function that takes a function like body and a collection like I's, and it iterates over all of I's, and it applies body to each of the elements inside I's, right? To return some output collection V's. And finally, we're going to call this library function sum that takes a list of doubles, which is now going to be this list V's, and adds them all up, reduces them into a single double. Okay? And so now this is where all the Floyd-Hoare stuff breaks down, because now you have to talk about collections, and Floyd-Hoare, it's really painful to talk about collections. The bigger problem is this body function and map. Like, what are we going to do over here? It's not what is called first order, because you have this lambda function or this closure that's passed into map, and things break down. Okay, and so here's where types really help. And let me, for this, it might help to have a little familiarity with types for this segment, but don't worry if you don't get it, because I'll be done with it pretty soon. Okay, so let's see now how our system analyzes code like this. Okay, so here's what's going to happen. The system takes the code, and during type checking, it essentially runs the type checker much like any modern language's type checker works. But instead of just doing the type checking, it also emits what we call horn constraints. Okay, and I'll explain what horn constraints are. These are logical constraints such that if you can solve these logical constraints and find a satisfying solution, and I'll explain what that is in a second, then it means your program is correct, which I'm going to denote with this little check. And if you can't solve this, then it means that your program is wrong. Okay, so when you can solve them, what it means is you've automatically inferred the appropriate types. And if you can't solve them, it means, sorry, boss, you don't have the right types. Your code is probably wrong. Okay, good. So let's see some examples of how the type checking works. So here's what's going to happen. So here, first of all, I say let I's is equal to range 0 length of x minus 1. And I'm going to assume that in my library, I have already given range the type that it says it takes n, it takes m, and it returns a list of integers between n and m, right? That's what this is saying. V, list of values v between n and m. So now what the type checker does is it says, oh, over here you're passing 0 for n, and this length minus 1 for m. And so the type of I's is going to look something like this. I's is a list of integers, all of which are greater than 0 and less than vlen x minus 1. Where did this vlen x minus 1 come from? That's what length of x returns, right? The length of x returns vlen x, and then we're doing a minus 1. Okay, great. Now let's look at this mysterious body, this lambda or closure, right? So body is strange because when we look at body, we don't know what inputs it's being called with. It takes some parameter I, and then it says x bang I squared. And so what I is this? So this is Alexander, right? You asked this question, how come we didn't have to write the refinement? So because the system doesn't know, what am I going to call body with? What precondition holds for I? So when the system doesn't know what the precondition is, it makes up a variable. So this is how my mom taught me to do algebra when I was, I don't know, 10, whatever age one learns how to do algebra. She said, whenever you don't know something, you introduce a variable, you call it x. Okay, so in this case, we make up a variable k, where k stands for the unknown refinement for I. So what I'm going to say is, or what the system says is, okay, I don't know what the input precondition is. And so I'm going to say that body is a function that takes as input some integer I such that k of I holds. The precondition is k of I. It's unknown what k is. We'll figure out what k is. Okay, and it returns a double. Why does it return a double? Because this x bang I produces a double, and then we're squaring it, so that's a double. Okay. What that means is that the type of I, again, is unknown at this point. It's unknown during type checking, is going to be I such that k of I is true. Okay, some fact k of I is going to be true. Now here's the key bit. Okay, so this is an idea that we've sort of borrowed that came much after Floyd-Hoare, but not that much, but still a long time ago. This was known from, the late 80s or the early 90s. This notion that people came up when they were building compiler analyses, where you might remember that what you say is that if you have a set of values P that flows into another variable Q, where flows is kind of nebulously defined, I'm not being very precise over here, what you can model that in a program analysis by saying that you get a set constraint that says the set of values that the variable P might hold is contained in the set of values that Q might hold. Why? Because, well, other things might flow into Q as well. And so you write a kind of subset relation P less than Q, right? And think of this is essentially, this idea lies at the heart of modern compiler analysis, right? This kind of, whenever you have values P flowing into Q, the set of values corresponding to P is a subset of those inside Q. So now what we do is we sort of generalize this with logic. What we say is, in that case, whatever fact holds about P implies whatever facts hold about Q. Okay, and this gives us what is called a horn constraint. So let's look at that back, in our example. Okay, so here there are two interesting flows. First, the variable I flows into the index that we're using for the array operation x bang I, right? So I flows into the index of x. And second, this collection i's that we created on line 1 over here, i's is equal to this range from 0 to blah, 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 flows into body. Okay, so this whole collection via the map operator is going to flow into and is going to give us the inputs that actually flow into body. Okay, so let's see what the corresponding horn constraints look like. And this I'm going to be a bit quick about. So the first flow, I flows into the array index for x. And so we get a horn constraint that says k of I, because I, remember, satisfies the invariant k of I, implies that I must be between 0 and less than vlen x, where this guy is the precondition for the array index operation. Okay. Next, let's look at the second constraint. The second flow here, I flows inside body. And so what that tells you is that, remember, here's the type that we've computed for i's. It was a set of integers such that each integer is between 0 and less than vlen of x minus 1. So we'll get a flow that says that this invariant, I between 0 and less than vlen of minus 1, implies k of I. Why implies k of I? Because that's the parameter that body takes, and that's the second flow that we get. Okay, so I'm collapsing a whole bunch of stuff over here, but roughly speaking, these are the two flows, the two interesting flows in this program, and they yield these two horn constraints. Okay, k of I implies that formula, and this other formula implies k of I. So now this looks like a bit of a chicken and egg problem. How can we possibly solve for k of I? And here we're going to use this third pillar from the programming, sort of the program analysis and programming languages literature, called fixed point computations or model checking, where essentially we can invoke the SMT solver and it computes what is called a least fixed point of this particular solution. This is what is called an abstract interpretation. And again, there's been decades of research on this, which I'm not going to try and summarize. I'll just tell you that these algorithms can produce a solution for this system of constraints that says, yes, if you set k of v to be the following formula, v greater than 0 and less than or equal to vlen of x minus 1, then that particular set of constraints becomes satisfiable, which means that all those implications work out. Okay, and since we found this particular solution, the system says, great, your code type checks, everything is great. Okay, and if you think about it, to answer Alexander's question, essentially this formula ends up becoming the type for body. You don't have to write it down because the system kind of synthesizes it for you. Okay, great. Let me pause here for a moment and see there's a question. Does vlen from the specification look the same as the length function? So this is a very interesting question that Artyom is asking. Oh, several people have asked this. Two people. How does that happen? Okay. It's an interesting question because in this specific example where I'm using vector, the actual code that implements the vector length is actually written in C. It's not even in Haskell, so it's outside my system. There's literally a foreign function interface. This is the kind of the secret of all modern languages, right? Which are type safe and so on. The way, if you really want speed, you implement your library in C. Okay, and so in the same way, that's what happens inside vector. So it actually implements these low-level arrays using kind of blocks of contiguous memory, but then exposes this clean kind of interface to the programmer, which is nice and functional and so on. So in this case, the length function, the actual length function for vector is written in C. And so I have to make up this fake, what programming languages let people like me and Harley call ghost, that describes what the actual size of the length is. But if we had in fact written the length function directly in the source language Haskell, which you might do in other data structures. For example, if you're building a tree, you might write a height that way. Or maybe we'll see an example later of where I show an interval set data structure where you describe the set of the collection of elements in the structure. Then in fact, yes, the logical specification is literally the same thing as your code specification. So to answer your question, Archam and Julia, in brief, in this case, they're actually slightly different because one of them is written in C and the other one exists purely at this kind of logical level. But in general, yes, they can literally be the same function. So for example, if this had been for lists, then we would have written the length function just natively in Haskell, and we would essentially be using that same definition for length. Okay, in order to find K, do you discharge to the SMT at each point, or do you do it completely for each file? Multiple. Oh, very good. So these are very good questions. These are very good questions. In fact, we do it for one whole file. So the way it works is you write a module, right, with, I don't know, let's just say 500 lines or whatever. And then the type checker goes over the whole module and it generates one whole blob of constraints. Just like creates a monstrous blob of constraints and hands them to the SMT solver. So now it's not accurate to say the whole constraints are handed to the SMT solver. There's this fixed point loop. And so what happens, you get this blob of constraints and there's an algorithm that sort of repeatedly issues queries to the SMT solver to solve these constraints. So for a particular file, there might be, I don't know, 500 constraints. And to solve those 500 constraints, we might make like literally tens of thousands of SMT solver queries. So they, in short, they happen sort of one module at a time. So one file at a time. If it is per site, how do you deal with multiple usages of KI? Excellent question. The short answer is that it all gets encoded in the constraints. If you have multiple usages of KI, then those multiple usages show up as multiple occurrences across different constraints. And so what you tell the system is, hey, here's one usage, and here's another usage, and here's a third usage. Find me a solution for K such that it's consistent with all three usages. Okay, so that's a very hand-wavy answer. But the details are that it shows up as multiple occurrences inside those K. Right. Okay. And in fact, it's a bit of a technical point, but when you have multiple things, you can kind of have conflicting usages of a function such that the types kind of get muddied and you get this kind of mixture owing to the different kinds of usages at different sites. Okay, let's move on next. And let me show you how you can take these same ideas and kind of generalize them to work on more user-defined properties. Oh, hang on, let me look at the time. 10:47, good Lord. Oh, well. Let's see how you can take these same ideas and now not look at just, array bounds checking or so on, but more interesting user-defined properties where maybe you create some bespoke data structure and you want to somehow enforce invariance about it. So as an example, I'm going to show you this cute data structure called an interval set, which is a data structure that represents sort of sets of integers by blocking them up. Okay, so here's what an interval set is. Whoops, sorry. Imagine I have a set of numbers 7, 1, 10, 3, etc., etc. Instead of just representing them as a kind of a collection of stray numbers like this, what you might do is first gather them up into a sequence. So if you look at it, I colored them so they're actually 1, 2, 3, 4, then 7, then 9 through 12. And then you take this whole sequence and you block it up into intervals. Okay, so 1 through 5, then 7 through 8, then 9 through 13. Okay, so they're kind of nicely ordered this way. And the convenient thing about this data structure is that if you maintain this order, then it allows you to compute union and intersection and membership, etc., pretty quickly. Okay, that's the high level bit. Okay, so now let's see how I might represent this particular data structure as a data type. Okay, so I would say 1, 5, 7, and 8. So what I have is, I say that this interval set is a data type which is either empty, okay, either the set is empty, or has a head interval, okay, that starts with some from. So for example, from 1 to 5, okay, so it starts at from 1 to 5, and then there's some tail, there's the rest of it. So it's a recursively defined data structure, much like a recursive list. We can think of this as a list where each element of the list has a pair of a from and a to interval, okay? So this is just your raw definition of a data type. You might represent this in Java, or Python, or Haskell, or whatever. Pretty much it would be the same thing, right? But now there were various interesting invariants that we are maintaining of this data structure that are very easy to kind of screw up in the course of programming with the data structure. So what are some of them? Well, we might want to say that each interval itself is non-empty. Okay, so I don't want to define empty intervals because that would be like a waste. Okay, I want to make sure that each interval is non-empty, because if the interval was empty, then I can just delete it. I don't even have to store it in my set. Okay, so the way I would specify that is I would say that whenever I have the to element, so in each head, when I have a from and a to, the to must be strictly greater than the from. Okay, so I don't want to have an interval from 1 to 1 because that would basically be the empty interval. Okay, here's the second one. I want to say that the intervals are in fact ordered. That's kind of crucial. The reason why intersection, union, and all that are fast, they're only fast if we can rely on the fact that the intervals are properly ordered, like in increasing order. Okay, and so the way you specify that is you say, okay, if I had from and to, then inside the tail, every element of the tail is a value v that is greater than 2. Okay, so I can't have, if I have the interval 1 to 5, then I can't put 3 in over there. Okay, so I must actually have everything occurring in increasing order. And that's it. So all we have to do is specify these two little things, and the system now can say, okay, I got it. If you try and create weird kind of interval sets, your code will get rejected. So for example, if you create an interval where the head starts at 8 and goes to 5, that's kind of junk because that's empty, because there are no values in that interval. The system will kind of complain, and if you flip it around, it'll say, oh, okay, that's fine, 5 to 8, that makes sense, right? Let's look at another example. I have an interval from 1 through 7 and 5 to 8, and this is bad because they're not disjoint, right? They're kind of overlapping, and we want to say that the intervals are disjoint. And so again, really, I made a kind of off by 1, so that should have been 1 through 5 and then 7 to 8. The system says, oh, okay, that's good. Here's yet another example. So these are in fact this is bad because it's not ordered. So this goes from 1 to 5, this goes from 9 to 13, and then this fellow goes back from 7 to 8. Okay, so somehow we've messed up the order. And so again, if you go back, the system doesn't like it, so it gives you this pink thing. And if you flip the order, then it'll say, oh, okay, I got it. Now it's all good. Okay. So of course, now it's interesting not just to check these kinds of intervals that I wrote by hand, but really what you want to do is verify implementations that are doing these various manipulations of intervals, computing the set, intersection, union, and so on and so forth. So let's see how this type inference that I showed you, with the Ks and the fixed point, makes verification super easy. So in fact, when I implemented this union operator for this particular data structure, I made this weird error, right? You don't have to understand the code. It is not important. The only thing that's important here is that there's a lot of intervals floating around. It's very easy to make little mistakes. So in this case, what had happened is I wrote T2 there and it should have been T1. And this violated one of these invariants about the data structure. And so I went to, I had to go back there and change that T2 back to a T1. And then the system was like, okay, yeah, now it's good. This is actually a valid interval, okay? And notice that the type system is letting me prove that if you give me a valid interval, 2 valid intervals, then their union is also a valid interval where all these invariants hold. Now, I really want to emphasize that this was not, the type system and the SMT solver did a lot of work here. So you might remember how I mentioned that another way to kind of prove these properties is to use proof assistants or interactive theorem provers. And I picked this particular example because my friend Joaquin Breitner actually implemented this in Coq, which is kind of one of the state-of-the-art interactive theorem provers. And he wrote the same kind of union implementation, but his proof was rather more involved. Okay, so he had to kind of spell out a whole bunch of intermediate steps. And it's the same theorem. It's the same thing that I was saying in the type. Good interval is1, good interval is2 means that the union is also good. And this was his proof. I mean, it goes on for a while. It's like, I think I forget, you can do the math on how many lines it is, right? Whereas in our code, it was just the code and nothing else. And the type system essentially just ground out and figured everything else out. Okay, so that's all I'm going to say about user-defined invariants. And now let's sort of, I want to show you how this enables very highly automated verification, right? So we built this tool when we've thrown it at a variety of different kind of programs. So many of these are kind of custom data structures. So XMonad is a nice styling window manager that uses this clever data structure called a stack set to actually manipulate windows. This is, so text and byte string are Haskell's libraries for manipulating UTF text and just like streams of bytes for, say, networking. And all of these essentially use very, very tricky low-level pointer arithmetic, where if you get it wrong, you will get buffer overflows. It's not speculation, right? You can easily get things like heartbleed and so on if you sort of mess up your pointer indices, because it's all actually implemented in C. And the type system is of no use. You can literally get Haskell code to segfault quite easily. And what we found is that in all of these cases, the extra specifications that we had to write, so these refinement types that are in those comments, were quite small. They were maybe about a line of spec per 10 lines of code. And in many of these cases, what we found is that the spec we were writing was already there in English as comments. They were just saying, please make sure this function is only called with arrays or strings that have XYZ property, right? Okay, great. So that's all I'm going to say about verification. It's very nice. It makes stuff very pleasant. I will definitely have to skip the proofs bit. I can talk about it offline if people like. But the nice thing is that all of this was using just the completely decidable, completely automatic SMT solvers fragment. If you like, and this is the stuff that I'm going to skip, you can now start writing, essentially start encoding pretty arbitrary correctness properties just by writing functions in your host language. And then you can use programs in your host language to prove those properties. So it's really quite cute. And we've done a bunch of cool things with it. But I will have to skip that because of time, okay? So the way it works out is that in theory, sort of with math, you have theorems, and you apply a theorem, and the way you apply a theorem when you're writing programs is you just call that function. The way that you, you do case splits inside a mathematical proof. When you're writing code, it just becomes an if then else. And the way you do induction in a kind of mathematical proof, when you're writing code, it just becomes plain recursion. So it's really quite nice. It gives you some very nice ways to sort of structure proofs. But we're going to skip all that stuff. We've used it to build a whole bunch of fun things that we'll have to sort of talk about at another time. So let me now sort of switch to the last part of the talk, which is what are some things that what are some lessons maybe that I've learned over the course of, working on this over the last, 10 or so years, right? So I'm going to sum it up with like 3 slogans, okay? The first, I'm slightly trolling over here, is that language is irrelevant, okay? And please notice the little foot mark over there. We'll talk about it in a second. Second is I'm going to make this very bold claim that verification itself is quite easy. And again, this is qualified. I will explain what I mean in a second. What I found is really, really hard is explaining when verification fails, okay? And let me sort of describe some of this in a bit more detail. So the first thing is not so much the language is irrelevant, but that the language is somewhat orthogonal to the thing that I showed you, okay? So again, somewhat, okay? It's not entirely, it's somewhat orthogonal. So what I mean is that the actual language in which you want to integrate the verification doesn't really matter what the host language is. All we really want is some basic sort of modern conveniences, let me just call it. You won't need functions, you need basic support for data types, you need basic support for sort of generic polymorphism. Now I should say there are some modern languages that do not support this feature, but the majority of modern languages do. For example, 10 years ago, there was just plain JavaScript, and there was a lot of stuff written in JavaScript, but then the good people at Microsoft came up with TypeScript, and modern TypeScript is really, really nice. It has a lot of cool support for all of this stuff. And it's quite easy to actually integrate, do this kind of language integrated verification. So the earliest version of this, of the machinery that I showed you was for a language called OCaml, which of course is an ML family function that has support for all of these. Then we did it for Haskell, but more interestingly, it turns out that you can take the same ideas and apply them to the context of C, where it's just very low-level programming with pointers. You have to do a fair bit of work to develop kind of the data types and so on, but it can work quite well. Then we did it for JavaScript, where you again have to add a little more type structure. And we did it for TypeScript, and a lot of this was, the TypeScript work now is maybe 5 or 6 years old, and it was in a much older version of TypeScript. Modern versions of TypeScript make this much easier with things like const and so on, right? And I think it's quite important that it be language independent, or really what I mean is it's like the mountain won't come to the prophet has to go to the mountain, right? We have to find ways to take these kinds of tools, these type systems, and put them inside kind of really widely used languages if we want people to use them at the same level as they do, say, profilers and GC and version control, et cetera, et cetera. Okay, the second point is that verification is easy. Now, what do I mean? So you might imagine, did I like cherry pick the examples? I did obviously cherry pick the examples for this talk, But really we found, and I've been teaching this, I've been teaching sort of classes with this material, and I think Harley also taught a class with some of this stuff. I'm surprised by how easy, new users find to use this kind of machinery, largely because of a lot of, just once you integrate the specifications inside the types, it becomes a very natural kind of process, right? It turns out that if you align the abstractions that the code is making, that the programmer is making in their design, with the abstractions that the analysis is making as it's trying to reason about the code, then everything becomes quite smooth. And many of the kind of rough edges, or the reason why a lot of program analyses were complex, was because, in my opinion, these abstractions were not necessarily aligned the right way. So for example, these were considered some classic difficult problems in program analysis. How do you find invariance? How do you do shape analysis? How do you reason about heap data structures? How do you do what is called context-sensitive reasoning, where a function has different behavior at different call sites? And it turns out that if you start using, for example, refinements on individual components, it becomes quite easy to guess what the refinements are in a way that it really, finding invariance is no longer really very challenging. Shape analysis similarly becomes really easy once you sort of work at the level of data types, as I showed you with the interval set. And similarly, the problem of context sensitive becomes a lot easier if you start associating refinements with type polymorphism, or just generic polymorphism, as you might see in Java or TypeScript or whatever. But what is really hard is the problem of explanation. And what do I mean by that? Well, the trouble is that the reason verification was easy is because we were doing all this stuff automatically. But automation is kind of a dangerous thing. Okay, so I like to use the word frenemy, because obviously we want automation so that we don't have to spell out all the proofs, as for example, poor Joaquim had to in that long cock proof. But what that means is that when automation fails, you're kind of left scratching your head. Okay, it can make it hard to explain to the programmer why exactly their code is wrong. So the simplest situation is when the code is wrong, right? So for example, in this binary search example, we were sort of scratching our heads until we discovered that, oh, there was an off by one over there, right? So why? Was it like just the red squiggles are not enough to tell you that there was an off by one? Somehow you want the system to say, maybe you should go and put in a little off by one check over there. But how do we do that? There's a couple of approaches. Maybe you can produce counterexamples. You can produce a test input that says, hey, look, if you run your binary search with the empty array, then it will crash. So that might be one approach that various people have looked at that might work out quite well. The second problem is that you have the wrong spec. So the code is actually fine. It's just the assumptions that you made about your preconditions or so on were not quite the right one. So this is a bit difficult to explain, but often, since we want the verification to all be very modular, we're going to reuse code from different libraries. And I don't know which, maybe I wrote a spec for the library that wasn't quite right. Maybe I needed to assume something else about how that library function behaved, and that was not in the spec. And so here I can't give you a counter example, because in fact, when you run the code, it's all correct. The theorem holds. It's just that the intermediate assumptions I made have to change. And so somehow you want new ways in which you can help the developer pinpoint, it's that specification that you need to go and fix. I need more information about how the map function works, or about how the range function works, or something like that. But the weirdest of all the problems is when the analysis itself is just quirky. And I wrote a whole little blog post explaining this thing, but I'll just show you this example. And all you need to take away from this example is that it's clearly strange. Okay, so here I'm writing an insertion sort routine. It doesn't really matter. Here's the sort function, takes a list and it returns a sorted list. Here's a function that checks that if I take an arbitrary list x's and I sort it, then the output list is actually sorted, right? So the check function checks that if you give me a list x1, x2, and some tail, then x1 is less than x2, and recursively, the tail is also sorted. And now if I look at this code, it's actually a correct insertion sort. So I don't know, the system doesn't like it. It says, sorry, I can't prove that assertion. It's not actually sorted. And it turns out that the fix is, here is to delete that particular type signature. Here, where we told the system that insert takes an integer and a list of integers and returns a list of sorted integers. If I delete the signature, then in fact, the system, watch this, I literally delete it, and then says, oh, in that case, actually your code is correct. And this is kind of mysterious. Why should it be that? I mean, this makes no sense whatsoever, right? Now, it makes no sense. I mean, it seems like it makes no sense, and really, let's face it, doesn't make sense. But actually, if you do the math, it turns out that that particular type signature where we said insert takes a list of integers was hobbling the analysis. And when we told the analysis, no, it's actually polymorphic. This works not just for integer lists, it works for any kind of list. Then it kind of, the analysis has a kind of Zen moment. It says, aha, various other things fall into place, which allow it to prove that check is in fact correct, right? That insert actually produces ordered lists. So I've explained this at length in a separate thing, which I'm happy to point you at later. But let's all agree that this is clearly strange and undesirable, right? And how on earth is a programmer to understand this? They really need a mental model of what the tool is doing. And I would argue that the biggest problem that language integrated verifiers or any kind of tool like this has is that all of these tools have a learning curve that looks something like this, okay? So here is time, and here is essentially your expertise, how quickly you are building up the mental model. So this is like this kind of plateau of frustration when nothing makes sense, you're just banging your head against the wall. And then roughly here is, the most people who use these kinds of tools are PhD students. Roughly here is maybe when you finish your PhD, so it's like at the 4-year mark or something, and then all of a sudden everything makes sense, right? You're like, oh, wait a minute, we have achieved enlightenment. And now, you can start doing amazing things. While really what we want is to make the learning curve more like that. Okay, so it's not so gradual. It's not so kind of steep. As you sort of play with the thing, you learn more and more and more about how it works, right? You don't just get this enlightenment at the very end, so that you're getting some value from it at the get-go. So how do we do this? I don't really know. This is a kind of an open question. I think one of the first things you want is, what kind of mistakes do people make in practice? And this is, we've done some work on trying to gather this just for regular type systems. What kinds of mistakes do programmers actually make? And can you target specific assistance for those kinds of errors? 2 is, can you build tools that actually make what the analysis is doing more transparent? Can you give it more information about, hey, if you only told me this, then various things would happen. If you only told me that, please help me here. That essentially help the developer understand where the analysis is losing information. But 3, I think really much of this comes down at the end of the day to just teaching. We have to somehow find new ways, new pedagogical means for explaining how some of these tools work. So I think ultimately we're going to need a combination of all these 3. Okay, so let me just stop there. I've already gone a few minutes over. So I told you why we want to do language integrated verification. I sketched out one approach for doing it using refinement types sort of baked into the language. And I told you about some of these challenges. If you, I should point out that there's a whole bunch of other groups that work on very, very related things. So here's, here's some of them that we draw a lot of inspiration from, and we kind of, we're all kind of bouncing ideas back and forth across all these tools like Daphne and F-star and Leon and so forth. And of course, all the actual work was done by, speaking of PhD students, done by my various PhD students, Pat and Nikki and Ming, Panosh, Alex, Ravi, and Eric. And with that, let me just stop. I think this URL, I can't remember if it's dead, but if you Google it, it'll show up. There's a lot more materials on this, but let me stop here and take some questions. Thank you. Ooh, I'm stuck on Harley. Sorry, let me just make this chat be everyone. There's some trick to it. Okay, yes. Thank you everyone. Thank you, Stefan. Thank you, Alexander and Christopher. Let's see, there's some questions. So let's see. Let me scroll up. What is DTT Harley F star? Blah, blah, great. Okay, good. So let's see. Back down to experience. What's the question? Does insert need to be polymorphic? That is exactly right, Stefan. You are absolutely right. So it needs to be polymorphic because I guess the short answer is that what I didn't realize is that polymorphism actually says a lot inside the type signature. So the fancy word that PL people like to use is parametricity. Parametricity says a lot inside the type signature. For example, specifically what insert says in this case, let me just go back. What insert says, if a polymorphic insert says that if you give me a value A and a list of A's, then I will give you back a list of A's, right? Now, implicitly, what parametricity is telling you is that the output list can only contain elements that were in the input list or the element A. It can't have any extra stuff inside it, okay? And this is the key bit of information that you need for the sorting to work out. Why? Because if you go back to the, maybe here, let me rewind. Oh, there's this little baby. Hang on. Hopefully you can still see my screen, but okay, let's go back over here. At this point where the recursive insert happens, where we say y, can I make this full screen? Where we say y const insert x, y's, what we want to know, what we need to know, oh gosh, is that the output of insert only contains a subset of the elements x and those that were already there in y's. And this, the polymorphic signature, kind of gives us for free. But the monomorphic signature says nothing of the sort, right? The monomorphic signature says, oh, it could be a list of any integer, you get back any other integer. Who knows what I did to produce the output list? It could be some other random list of integers, right? But the polymorphic signature just gave us that information for free. And the type system was able to, essentially, the way the constraints get generated, it sort of picks up that information and is able to use it to verify the code, right? So Stefan, to answer, the short answer to your question is yes. And that is the same reason why for the interval set, I also used a polymorphic signature. Okay, so that's a very, very sharp observation. Okay, let's see. Edward, you said that your tool was language. No, the tool is not language agnostic. Let me take that back. The ideas are language agnostic. The tool, the specific tool that I'm showing you in the slide is very, very hardwired to the Haskell language. Hopefully, let me make that very clear. The ideas are language agnostic in that this general philosophy of language integrated verification, with a fair bit of work and a lot of elbow grease, you can make it work for other languages. Haskell is especially nice because you don't have to fight it. It's kind of already set up where a lot of this stuff just works out of the box. I don't have to make up a new type system for generics and so on and so on because it's just there. But for these other languages, you have to do some of that. But many of these other languages like Java and TypeScript notably are sort of increasingly becoming more Haskell-like in that they have natural support for, generics. They have, the TypeScript has nice support for algebraic data types now. So much of this will probably become much more pleasant. But the actual tool itself, you cannot use on other languages at all. You can only use on Haskell. Oh, Piyush is sad to report the refinement types doesn't work. Probably my credit card expired. If you just Google refinement types, you know what? I'll paste it in the chat. How about that? I can just, Peter Sewell, your examples were mostly data structure libraries. What can you say about the experience of doing this on larger, more diverse bodies of code? That's a very good question, Peter. All the examples I showed in this particular talk were in fact data structure libraries. My sense is that the convenient thing about data structure libraries is that it's very easy to come up with sort of nice specifications and various invariants for them. So I don't think it's more that the method is suited for data structure libraries. It's just that they're very convenient for showing off nice pre and post condition, nice refinements. Very recently, actually, when I say very, I literally mean yesterday. My students and I, wait, this is kind of violating double blind, whatever. We just wrote a paper on how you can use refinement types, the same tool, to do something quite different. There's no data structures. Well, I guess in the end, everything is a data structure, but there are no data structures really for enforcing information flow control properties on web applications. So imagine the kind of web application like, Hotcrap, right? Where you sort of submit papers and reviewers see them and so on and so forth. And there the specifications are quite different. So these are now sort of information access properties. So there are no data structure invariants of this where there's sort of this weird recursion and so on and so forth. The invariants are all properties of the form that say certain parts of your database should only be viewed by certain kinds of users, right? And what we found is that this was a very natural fit. I mean, it took a lot of work to make all the pieces kind of fit together. And so we found that quite nice. In another recent piece of work, what I did is I ported a lot of, the software foundation style of work, but actually closer to something you might be familiar with, which is Tobias Nitkov and Klein's Concrete Semantics textbook, right? Where they sort of develop formal semantics using Isabelle. So I took that and I sort of ported it to use refinement types. And I found that to also be quite a pleasant experience. So I guess the short answer to your question is, I think with a fair bit of, we've sort of focused on data structures largely because it's just a convenient source of specifications. You have a binomial heap and it has all these weird invariants that you want to enforce. But over time, we've sort of gradually expanded out into these other things where, things are quite pleasant. That being said, there is one thing that I'm very unhappy about, where I think we have not really found a convenient way to do this, is when you have highly effectful computations, where there's a, if you, the mixture of higher order and state, our specific approach is really, it's quite kludgy and painful. Like with all the pure code I showed you, it's just very nice. Everything just works beautifully. The moment you have higher order and state, things get very complicated. The F-star people, various people have mentioned them, I had them on a slide, have a whole line of work on, reasoning about higher order and state. I mean, to my taste, it is still very complicated. So I don't think we've really cracked that particular puzzle very well yet. How do you make reasoning about imperative computations quite as pleasant as reasoning about pure computations? But maybe that's fundamental. Maybe that's the reason why people should be writing purely functional code. Oh gosh, hang on. It says my battery is going to die. Let me plug in my power. So I don't know if that really answers your question, Peter, but I think this is one of the things we just need more experience with. Let's see, Stefan got it, forget the user specified. Yes, so that is exactly, so correct, Stefan. So I agree with you. In the specific way the tool works is it always uses, we never try to override any types that the user wrote. So if you wrote this, then we're going to start with the int spec. And that's why when you delete it, GHC automatically gives you the polymorphic spec. And that's why it all works out, right? So there's this kind of cascading dominoes, collection of dominoes. In the insert function, is there a way to make it monomorphic to int, but allow, why? Yes, there is. There is in fact such a way. I'll point you to a paper that we wrote that was specifically about this problem, where essentially with polymorphic, with generic types, you get a lot of fun stuff, but sometimes you really want that to work even with monomorphic types like int, right? And so this is a method of what we call abstract refinement types. So if you Google that particular expression, abstract refinement types, you would get a signature where, just like, think of polymorphism as, when I say something is of type A, arrow, A, arrow, A, what I'm saying is that for any A, if you give me two A's, I will give you back an A. We can play the same trick with refinements, where what we say is something like, for any refinement P, if you give me two integers that satisfy the refinement P, then I will give you back an integer that satisfies the refinement P, right? And that's, in a nutshell, how that particular technique works. And oddly, it connects with what with my answer to Peter, because the way the whole information flow system works is it sort of crucially relies on that particular method. So I didn't talk about it here, but the short answer is yes, there is a way. It's very nice if I say so myself. And I can point you to it in a sec. But if you just Google abstract refinement types, you'll see it. I was thinking, so think of abstract refinements as like, just like you have types and you have type polymorphism, you can imagine refinements and then refinement polymorphism. And so it's a way of getting polymorphic refinements. I was thinking of your slide that showed you had applied this to, no worries, Edward. To get only designer, how do you limit the form of allowed specifications? Oh, excellent, Ugo. So the way we do that is we just tightly control the language of what you're allowed to say in your specs, right? So the grammar, literally the grammar of what appears inside refinements is very rigidly controlled to just belong in this logic, right? So specifically, we define a kind of, this is the kind of what the SMT people call this, uninterpreted functions, linear integer arithmetic. You can throw in a few other theories like sets, bit vectors, strings. These are all kind of happy and decidable, and so on. And then for everything else, we use what is this magic escape hatch called an uninterpreted function. So you saw how I said VLAN over there. So VLAN is what in the sort of logic community they call an uninterpreted function, which means that the only thing you know about VLAN is that if x equals y, then VLAN of x equals VLAN of y. That's all. So this is what is called the axiom of congruence. And it turns out SMT solvers are great at this. And this goes back to, the original decision procedure for this was invented by Ackermann, and it is in fact the Ackermann of Ackermann's function. But anyway, so uninterpreted functions are this great escape hatch where you can encode things like lengths and so on. And then, in this work where I talk about, you can now start talking about arbitrary proofs. We essentially open that escape hatch a little bit, where we can say, oh, look, these functions need not be entirely uninterpreted. We can actually have some interpretations from them, which are derived from the user-defined implementations. And that's how we sort of slightly relax this decidability limit, if that makes sense. Okay, 3 new messages. Why would it not just show me the messages? Peter, Artyom, you mentioned that young people are pretty good with them. Have you tried? Yes, I have. So this is Artyom. I've used it a couple of years. I've been gradually, one of my favorite examples that I find it very cute, is where we define like a small imperative language. It's on one of, in the non-functioning refinement types, website, I think you can follow it, right? Where we define a small kind of imperative language, variables, assignments, loops, if then else, etc., etc. And then, you know how you write the usual interpreter for it, right? Usual interpreter and so on. But you want to make sure that every variable is defined before use, right? Because if it's not, then the interpreter, when it tries to read the value of X, is like, oh, I don't know what X is, it's not in my store. And so you get a runtime exception in the interpreter. And so then what this assignment does is it shows how you can represent this defined before use essentially as logical functions, much like this VLAN that I just showed you, where you define, these are the variables that are getting defined in your code. These are the variables that are getting used in your code. And this is how you define definition before use. And now you can kind of, at compile time, guarantee that if you only pass in to the interpreter well-formed expressions, then it will, it will not crash, right? That sort of, you essentially build a diffuse analysis and you use it at compile time to verify that your code will not crash. I thought it was quite cute. And I left this as a kind of challenge problem, and I was surprised by how many students had, found it quite easy to, this is what you do. It's pretty straightforward. So I have tried it with students. Students have found it, I have found much of it quite easy. So to my surprise, I mean, the things they found irritating are actually, being able to download and install the tool itself, which I think has gotten a bit better with time. Your comment about effectful, is it also the case, Levent asks, hi Levent, is it also if I structure my program around Haskell definable monads? I meant both. The moment you have, I don't know. I don't know how to make this more precise, Levent. I mean, for example, in this, the thing I just described to you, I just talked about this web application thing. There is a monad, right? So if you've ever used any of the Haskell web frameworks like, Scotty or Spock or any of those, there's ultimately it's a monad, and everything is done using a monad. What I meant is, I meant mostly reasoning with references. So once you have references and you want to reason very precisely about what references are doing, like if you have, for example, let me just tell you the kind of standard criticism which one might make going back to the data structures. So all the data structures I showed you, they're like pure data structures, they're completely algebraic, et cetera, et cetera. If you do the same things and start implementing them with low-level kind of pointer manipulation and pointer swizzling, everything becomes much harder, right? You need all the stuff with separation logic, and you need a lot of complexity, which the F-star people have found. It's possible, you can do it. It's just not as kind of, it's not as smooth as just like we write the type definition and everything just works out. It's just a lot more work. So anyway, what I think the short answer is, I think references, maybe I should be more precise. It's references that are really painful. I don't know if that really answers your question though. Okay. Thank you, Levent. Okay.
Great. So does anyone else have any questions? Sorry, were you going to say something?
No, I'm happy to stick around if people want to ask other things. What is it, 11:20? But I think we're out of time. I leave it up to you to decide, Harley.
Yeah, I mean, if everyone's done with their questions, I think we'll just go ahead and conclude now.
Okay, well, thank you very much. Thanks again. This was a real blast.
Thank you. Yeah, it was a great talk.
Thanks very much.
Yeah.
Thank you, everyone. Have a nice weekend. Stop the share.